Hi everyone, in this video we're going to start topic 10 and we're going to discuss intermolecular forces and physical changes and how they relate to this. So we talked in the last topic about intramolecular forces and we talked about how we can name these differently, but we had kind of foreshadowed what we were going to talk about this topic, which is intermolecular forces. We had talked about how water, whenever it freezes, actually expands and it gets further apart, whereas all other substances, when you freeze them, they become more dense. So when you go from a liquid to a solid with other substances, they become closer together. But when you go from a liquid to a solid with water, it actually gets less dense. So the thing that's causing solid water to expand is our intermolecular force. So water itself has this specific type of intramolecular force here between our hydrogens and oxygens. And as you all know, this is quite a strong force. It's almost ionic. It has a very high dipole moment or a large dipole moment. But between these water molecules, so we have one water molecule and we have another water molecule in solution. Because when you have a drop of water, there's a bunch of molecules inside of it. And these things are actually connected by what we call intermolecular forces. The name of this type of intermolecular force in water is actually called hydrogen bonding, and it's extremely strong. Because water has a strong intramolecular force, it also has a strong intermolecular force. So what's happening here is these partial positives between the dipoles here and partial negatives are highly attractive in their liquid state or solid state or gas state, whatever state they're in. So what happens here, which is really unique, is that these water molecules push each other around because of their strong polarity. So because one of them is partially positive and one of them is partially negative, and they're very strongly positive and negative, they require that they're lined up together. Positive must be stuck to the negative end. So in a lot of other molecules that have smaller dipoles, that's not quite so important. Like sometimes it can be together, sometimes it's not. But in water, it's really, really important that they line up because of the strength of these differences in dipole moments. So what this kind of looks like in solution is that these waters have intermolecular forces between them. And they're actually quite rigid. So this is a good example of water as a liquid. And you can see here that your partial positives are stuck to your partial negatives. And when one of them moves, it moves another one because they're all kind of stuck together in this network. And so what happens when you freeze water, it does this really cool thing. So what's happening is that when you freeze water and you cool it down, this movement between the water molecules becomes less. So when you have more heat, think about it. As you heat something up, it can move a lot faster. As you cool it down, it's going to move a lot slower. We learned about this with gas laws. And the same thing happens with liquids and solids. So as you cool something from a liquid to a solid, it's going to move even slower. And so what this means is it's really important now that the molecules line up. Because if they don't line up, you're going to have a mishmash of the forces here, and they aren't going to like it. So what happens is when water is a liquid, or when H2O is a liquid, we see that sometimes it lines up, sometimes it doesn't. It moves quickly enough that it can reorient itself as needed. Whereas when H2O is in its ice form, when it's a solid, we're seeing that it turns into this crystalline structure where the hydrogens must be lined up with the oxygens. And so what that does is it forces them apart because they don't have so much room to move around anymore. They have to be lined up in a certain way. So this equal spacing in order is forced between the molecules, which is why water is less dense as a solid than it is as a liquid. So they actually move. So water is one of our few substances that does this. There aren't too many other ones that are going to expand as they become a solid. So I like to talk about water because it is the basis of life on this world, and it has so many unique properties. You wouldn't think about it, but hydrogen bonded to oxygen is really something special. And it does a lot of unique things. So let's talk about the difference here between intramolecular forces and intermolecular forces. Let's go ahead and define this since we quite haven't done that yet. So intramolecular forces that we learned about in topic 9 are forces that hold atoms together and they are inside of a molecule. So here's an example of your intramolecular attraction. So these are chemical bonds. That's what we would call chemical bonds. So things like our nonpolar covalent bond, polar covalent bond, ionic bonds, those are intramolecular forces. Now we have intermolecular forces that are forces that exist between molecules. So they aren't inside of a molecule, but they're between two or more molecules. And so we're seeing these temporary connections here, these intermolecular interactions, where the positive side of molecules are lining up with the negative side of molecules. And we did talk about this a little bit actually in your gas laws lab. We had discussed some intermolecular forces. So this is where this is going to come in a little more. All right, so now I'm going to ask you to make sure that you understand this concept. So what is the main difference between intramolecular forces and intermolecular forces? So the difference we're looking for here is that intramolecular forces are inside of atoms, or inside of molecules, and intermolecular forces are between molecules. So they're kind of outside of the molecule, between or outside. Okay, that's our difference there. One's an internal force and one is an external force. Let's take a look at the different types of intermolecular forces. We had talked about our different types of intramolecular force, our nonpolar covalent bond, polar covalent bond, and ionic bond. Intermolecular forces, we have 4 different kinds we're going to talk about. The first one is ionic. So this is a little weird, right? Because I told you that ionic is an intramolecular force. Ionic is weird. It's such a strong force that it's both an inter and intramolecular force. And we're going to cover that in just a minute. Hydrogen bonding is our next most strong intermolecular force because it's very polar. A good example of hydrogen bonding is in our water molecules. Dipole-dipole is the next type of intermolecular forces that we talk about. And it is a medium strength. It's less than hydrogen bonding. It's not as strong as hydrogen bonding, but it's stronger than our last type of intermolecular force, which is London dispersion forces, or you might have heard them called van der Waals. Those are the same terms, so don't get those mixed up. And these are very weak forces. They often occur in nonpolar compounds, but they can occur in compounds that are really close to nonpolar as well. Okay. So let's talk about ionic bonding. We're going to start here with the strongest intermolecular force. Ionic bonding is both intra and inter. It's both, yes. So what you see here is an ionic crystal. This would be your chlorine, and then this would be your sodium here, your negative and your positive. So remember the difference between intra and intermolecular forces. One is inside of a molecule and the other one is outside of a molecule. Well, here those are the same thing. So the force between this is both inside of a molecule and also outside of another set of molecules. There's no clear way to say that's either inside or outside of a molecule, which means it's both. Remember that with our ionic bonding, we have electrons that are sequestered by only one atom only. So in this case, chlorine takes all of them, and sodium is left with no valence electrons. So it takes an electron from sodium in order to gain its full octet. The other thing that we saw is that there's no distinction between ions of the same molecule or ions of a nearby molecule because salts occur in these crystalline structures with these crystal lattices. And it's just not clear where one molecule starts and the other one stops. It's just one big continuous structure. So we don't have that distinction. So they come in a highly ordered lattice atomic structure. It's highly ordered because of the positive and negative charges, and they must be connected. A positive must be connected to a negative and vice versa. You won't ever see two negatives stuck together, two positives stuck together. So just to reiterate, the type of intramolecular force here is ionic. The type of intermolecular force is ionic. So if you all remember this chart from topic 9, that's how you know what type of intramolecular force exists, is by looking at the electronegativity difference. So these are both ionic. Let's take a look at hydrogen bonding. So hydrogen bonding is our next strongest IMF. So when we were talking about molecular compounds, so for molecular compounds, it is the strongest intermolecular force. Remember that molecular compounds are two nonmetals, or two nonmetals. So something like H2O. I'm going to be abbreviating intermolecular forces as IMF from now on, so that is what that means. Hydrogen bonding is very specific. It only occurs when there is a hydrogen and it is attached to one of three atoms, a nitrogen, an oxygen, or fluorine. So what other molecules besides our water can have hydrogen bonds? What other things might we be looking at here? There are only going to be two other ones that can exist. So the only other types of molecules that can have hydrogen bonds on them are ones where we have our H stuck to an N or our hydrogen stuck to a fluorine. That's the only scenario in which you'll see this. So normally we see this with ammonia. So this is, ammonia is typically in our Windex cleaner, so that smell, that's ammonia. This water. And then hydrofluoric acid, you will also see hydrogen bonding. So I don't know if any of you have seen Breaking Bad. Yeah, but he dissolves like a body in hydrofluoric acid, so I thought I would put that reference there to help you remember that it is a really strong bond. This is actually a very dangerous chemical because of its big electronegativity difference. It's highly reactive, and it has these really strong attractive forces between it. Okay, so let's take a look at our overview. So the type of intermolecular force in, say, water here is hydrogen bonding. What about our intramolecular force? What kind of intramolecular force is in a molecule that has hydrogen bonding? What you're going to find is that they're going to fall in this range here. So molecules that have hydrogen bonding, that's their type of intermolecular force, but the type of intramolecular force that they exhibit is polar covalent. So we determine our intermolecular forces based on our intramolecular forces, is what I'm trying to show you here. So in order to determine intermolecular forces, you really need to also know the intramolecular forces. Let's take a look at the next type of intermolecular force, which is dipole-dipole. This is our medium strength intermolecular force. It's kind of in between hydrogen bonding and the weakest one, which is London dispersion forces, or van der Waals. So whenever you have a dipole-dipole compound, we do have partial positive and partial negative charges on these. They just aren't as strong. There's a smaller difference here than there would be, say, with water and oxygen. This is a much bigger difference in electronegativity here. So we do see that these charges align, where the negatives kind of line up with positives. So the type of intermolecular force we're seeing here is dipole-dipole. Now I'm going to ask you to determine the type of intramolecular force that exists in this compound. You may need a Pauling scale, or you might be able to remember based on all of our examples that we've done. So if you take a look at dipole-dipole, what you're going to find is the electronegativity difference here falls in this polar covalent range. Okay. So we see that both hydrogen bonding and dipole-dipole bonding are a result of polar covalent bonds. But the difference is that our hydrogen bonding is specifically between a hydrogen and an oxygen, a hydrogen and a nitrogen, and a hydrogen and a fluorine only. You will never see it with anything else. So do keep that distinction in mind as you're learning these. Let's take a look at our last type of intermolecular force, which is London dispersion forces. This is the weakest intermolecular force we're going to talk about. And it occurs under two circumstances. One, when you have a nonpolar compound, so when your intramolecular force between your atoms is nonpolar, which we're going to find here. This one, there's an electronegativity difference of 0. So that definitely means it's nonpolar covalent. This intramolecular force is nonpolar covalent. But there's another scenario in which this happens. So you can have a bond that is polar covalent, but your molecule has London dispersion forces. This occurs whenever you have no net dipole and all of your forces cancel out. Remember, in order to have this attraction with this dipole-dipole force that we learned about, we need a partial positive and a partial negative end. Well, if we have no net dipole, we don't have a partial positive and a partial negative end. They've been canceled out. So we can take a look at, say, this molecule here. So if we drew our dipole moment arrows on here, we draw them like this. We saw that this is a polar covalent intramolecular force. However, they all cancel, meaning that there's not really a distinctive positive or negative end to this molecule. So that means it interacts with other molecules of its kind very weakly because there's not really a partial positive, partial negative end for it to stick to. So you can see that difference kind of highlighted in this molecule here. So this is acetone. Actually, we used it in our in-class lab. And you can see when we've got carbons, carbons, and an oxygen, we have a clear partial negative and partial positive end on this molecule. Whereas, say we took this oxygen and we turned it into a CH3, now we've got a CH3, CH3, CH3. This is a carbon in here. And they all cancel each other out. They're all the same. This pulling between things is exactly the same. So this one is nonpolar covalent, and it has London dispersion forces. Whereas this one is nonpolar covalent. It has both London dispersion forces and a dipole-dipole force. So this right here is dipole-dipole. But these things right here have London dispersion forces. Okay. So even though this is the weakest intermolecular force, to me personally, I feel like it's the most complicated because there are so many exceptions. So you need to be careful here when you are looking at intramolecular bonds and what type of intermolecular force that corresponds to whenever you see kind of like a symmetry in a molecule and all your dipole moments are canceling out. So an intramolecular force that has London dispersion forces as their intermolecular force could be a nonpolar covalent bond. It could also have a polar covalent bond, but it has to have no net dipole if it has the polar covalent. So you could have nonpolar covalent and it have a net dipole and it would still be London dispersion forces. But if you have a polar covalent bond, it has to have no net dipole in order for it to qualify as London dispersion forces. Okay. So let's look at how these London dispersion forces actually work on a molecular level, because these are the weakest type of electronegativity differences and attractive forces here. They actually aren't very strong, but they still attract. So the question is how? How do they do that if all the forces are evenly canceled out and there's no overall like net force? So the deal here is that with all molecules, as we've been learning, and all atoms, these things are not stagnant. They're constantly moving around. Electrons are constantly buzzing around atoms. And at some point, sometimes electrons just happen to be more on one side of the molecule than the other, or happen to be more on one side of the atom than the other. And this is completely random. And so when that happens, if one molecule lines up more, all the electrons are on the side, that means the next one's going to line up with all of its electrons on the side. And it's going to try to replicate that as much as it can. That's its attractive force. And so this is what we call a temporary dipole. Whenever it just happens, there is a point in time where all of the electrons kind of shift to one side of the molecule. And so this is represented here with this, this double partial negative, indicating it's a really, really weak negative charge. This is your double partial positive, so it's really weakly positive. So that's essentially what's happening here with London dispersion forces. As you have more and more electrons in a structure, so the CH4 has a decent amount of electrons in it. Let's see, let's look at helium. If we just had helium and helium stuck together, they only have 2 electrons in them, so this would be your helium. It's got a double bond in it. It only has 4 electrons. So if we were to look at the London dispersion picture of helium, you'd only have 1, 2, 3, 4 electrons in it. So if it formed a temporary dipole, kind of all 4 of these would be more to one side, and they'd line up. What you're going to notice here is that this is a weaker force than the CH4 when it forms a temporary dipole here, just because it has more electrons. So this would be a stronger London dispersion force, and this would be a weaker London dispersion force, just because one has more electrons than the other, or one has less electrons than the other. And remember, electrons are negatively charged. So if you have more electrons, you have more negative charges, and therefore more attractive force can occur in between these molecules. So here's a summary of all of the different types of intermolecular forces we've learned and intramolecular forces and what they correspond to. So our ionic bonding is both an inter and intramolecular force. It occurs when you have an electronegativity difference of 2 or greater. It is the strongest. We also know that sometimes ionic compounds can fall in this gray area between 1.6 and 2.0, but most of the time it's going to be this 2.0 or greater. Then we have our hydrogen bonding, which occurs with polar covalent compounds only, and they need to fall in this electronegativity difference to register as polar covalent intramolecular forces. This is the next most strong intermolecular force that we have. Then dipole-dipole is next. It occurs with polar covalent compounds as well. So it's going to be in this electronegativity difference, and it's weaker. Remember that hydrogen bonding only occurs between hydrogens and oxygens, hydrogens and nitrogens, and hydrogens and fluorines. It is very specific. And dipole-dipole is everything else that has a polar covalent intramolecular force. London dispersion forces are our weakest type of intermolecular force, and they can occur with 2 different types of intramolecular forces. You can have nonpolar covalent force, which is this 0 to 0.5, or you might have polar covalent bonds, but the molecule must have no net dipole if it has polar covalent bonds, or it's not going to qualify. So you can have nonpolar, and it can have a dipole, has dipole, or it doesn't have to have a dipole, has dipole, or does not. It doesn't really matter with nonpolar covalent bonds. It will always qualify as London dispersion forces if that's all it has in it. But if it has a polar covalent bond, it might qualify as dipole-dipole unless the molecule has no net dipole overall. So do keep in mind that when you're learning this kind of stuff, that molecules can have more than one type of intramolecular force or intermolecular forces. So this is a good example. This is ethanol. So I put them this way to kind of show they're floating around in solution all together. We can see that we have different types of forces going on here. All right, we've got this force, that force. And then we also have these forces here. Okay. If we went in to qualify the electronegativity differences on all of these different dipole moment arrows, you find that this one qualifies as nonpolar covalent, this one qualifies as polar covalent, this one qualifies as polar covalent. If you went in to qualify the intermolecular forces corresponding to these, you find that this is a London dispersion force. Because this is polar and it's not between a hydrogen and a nitrogen, a hydrogen and oxygen, hydrogen and fluorine, it means it is dipole-dipole. This one here is a hydrogen bond because it's between an oxygen and a hydrogen. Hydrogen bonds are really easy to spot. Okay, so this one has 3 different types of intermolecular forces and has 2 different types of intramolecular forces. So these molecules here interact with each other through hydrogen bonds, dipole-dipole bonds, and London dispersion forces. So now I'm going to ask you to apply this knowledge that you've learned. So use these compounds over here and fill in the following table. I'm going to ask you to, for this one, we're going to label this A, B. I know that Edpuzzle can be kind of difficult. Okay, so for molecule A, let me know what the intramolecular force is and the intermolecular force is for that compound. And then for B, the 2 bromines, what's the intramolecular force and the intermolecular force? And for C, what is the intramolecular force and intermolecular force? I've left you this chart down here that might help. You may need a Pauling scale for this as well. Remember that some of these may have more than one type of force. So let's take a look at how to answer this one. So the intramolecular force here for this one is definitely ionic because we can see this positive and negative charge here. We see the electrons are not shared in this compound, which is a dead giveaway that this is an ionic intramolecular force. If you calculate the differences in your forces here, it's going to either fall in this category or in between these categories. So because it's intramolecular, that ionic, that means our intermolecular force is also ionic. For B, the 2 bromines, if we look here at our electronegativity difference, it has an electronegativity difference of 0, meaning it's definitely nonpolar covalent, which means the only type of intermolecular force it has is London dispersion forces. And then this last one, C, is exactly the same as the example that we did. It's got this type of force here, this type of force here, and then it's got a type of force between our carbons and hydrogens. There's also between the carbons and carbons, but that's an electronegativity of difference of 0. So we're going to see that this one has both nonpolar and polar covalent bonds. The intermolecular force for this one is London dispersion force between the carbons and the hydrogens and the carbons and the carbons. Then we have a dipole-dipole between the carbon and the oxygen. That's how it's going to interact with other molecules there. And then we have hydrogen bonding, where the OH is going to interact with other OH groups in similar molecules. Now I'm going to ask you to do a couple more advanced examples because these things can get complicated. So see if you can answer the same questions here for these new molecules, A, B, and C. So the intramolecular force for this first one, we're going to need to look at the differences here between our carbons and our fluorines, and then our carbons and our hydrogens. Carbons and hydrogens are always nonpolar covalent. That might help you to remember because a lot of organic molecules are made up of carbons and hydrogens. So anytime you see those, it's just London dispersion forces, point blank. So that will help you kind of narrow that down. Between our carbon and our fluorine, so if we look at the electronegativity of carbon and fluorine in a Pauling scale, we see carbon is 2.55 and fluorine is 3.98. That's going to fall in this range here. I think it's like 1.4 is the difference. So that's a polar covalent bond. So we have nonpolar covalent and polar covalent. Now if we want to know the type of intermolecular force, we're going to see what corresponds to that. So our nonpolar covalent is London dispersion forces. Our polar covalent can be either dipole-dipole or hydrogen bonding. We see that the fluorine here is not stuck to a hydrogen, it's stuck to a carbon, so it must be dipole-dipole. So for the next one, we've got a sulfur and an oxygen. We can go to our Pauling scale, and we're going to see that the difference here is going to fall in this polar covalent category. It's polar covalent. Yay. Right. Now, in order to find the type of intermolecular force, because it's polar covalent, we would think that it is either dipole-dipole or hydrogen bonding. The oxygen here is stuck to a sulfur, not a hydrogen, so it's not hydrogen bonding. So this would be dipole-dipole. However, we need to take a closer look at this molecule. It is symmetrical. Its dipole moment arrows all cancel out, meaning that it would have dipole-dipole if it was not symmetrical, but because it is symmetrical, it only exhibits London dispersion forces. That's it. Because they all cancel each other out. So even though these are pulling relatively strong because they're polar covalent, they all negate each other. So if there was another SO3 molecule around, these things would interact a lot less than if it was a polar, if it had a net dipole and it was a polar compound. This is nonpolar. So that's one of those exceptions. Let's take a look at C. So C, we've got sodium, and then we've got this nitrate ion here. Well, nitrate's not on the Pauling scale, right? It's a polyatomic ion. It's not on the Pauling scale. So what we need to look at here is how these electrons here are not shared. If these electrons were shared, there would be a chemical bond like these drawn in between them, and there just isn't. The bond here is definitely ionic, and it's shown in the charges, how we have a separation of charge, a positive and a negative. In our molecular compounds, we can only have partial negatives and partial positives. You won't see full negatives and full positive charges. So it stands out that this is an ionic compound, and therefore the intra and intermolecular forces are the same.